it's me again. Again, if you see my face in a video, you know that it's important because I'm trying to find videos, and there's tons of them online that I could show you with Khan Academy. But when you see my face, you really need to watch the video over and over and over. Now, last week, I did throw in a question on the quiz about the tangent of a 45-degree angle, and the answer to it was hidden in the video that had my face on it. But I'm going to clarify that today because several made that mistake, said, well, there's not enough information to determine the tangent of a 45-degree angle. But if you remember that video, it said it's not the size of the triangle that matters, it's the size of the angle. So today what I'm going to do is review two concepts from Euclidean geometry, the concepts of two special right triangles. There are two special right triangles in geometry. There's the 45-45 90-degree right triangle, and there's the 30-60 90-degree right triangle. And the reason why these are special right triangles is because, well, every right triangle that exists, if you know two sides, you can find the missing third side by using the Pythagorean theorem. But with these two special right triangles, you only need to know one of their sides to find the other missing two, if you need to, and you don't have to use the Pythagorean theorem because their sides are, there's a relationship between them that exists beyond the Pythagorean theorem. But we can use that to prove what the relationship is. For example, in a 45-45 90-degree right triangle, every single 45-45 90-degree triangle that exists in the universe, they're similar to each other by the angle-angle similarity postulate. You might not remember that because, I love some geometry, but basically, if two angles of one triangle are congruent or equal to two angles of another triangle, then those two triangles are similar. Same shape, but they may differ in size. So when we look at this, we know by the isosceles triangle theorem that whatever the length of this side is, we'll just call it x, then this side's going to have the same length. Two congruent angles, two congruent opposite sides. Now we still don't know what the length of this one is, so we'll call it a different variable, y. But what I'm going to do is use the Pythagorean theorem to rewrite y in terms of x. So in other words, x squared plus x squared equals y squared. I've got 2x squared that equals y squared. And now let me take the square root of both sides. And since we're dealing with distance, I'll only deal with the positive aspect of the square root. So this will be take the square root of that and take the square root of that. So the square root of 2x squared is x times the square root of 2. So now I can rewrite and change y as x square roots of 2. So in every 45-45 90-degree triangle that exists in the universe, the sides are going to follow this relationship. X square roots of 2. Or in other words, if I have a 45-45 90-degree right triangle, if this side is 6 feet, this side will be 6 feet, this side will be 6 times the square root of 2 feet. If it's 16 feet, this one will be 16 feet, and this one will be 16 times the square root of 2 feet. So in other words, when I ask for the tangent of a 45-degree angle, tangent, some old hippie called another hippie, tripping on apples, tangent is opposite over adjacent. So the tangent of this 45-degree angle is x over x, which is 1. The tangent of this 45-degree angle is opposite over adjacent, x over x, which is 1. The tangent of this 45-degree angle is 16 feet over 16 feet, which is 1. So it's not the size of the triangle, because remember, we're dealing with trigonometric ratios, a comparison between two numbers. So yeah, this side 16 feet over 16 feet may be shorter than 116 feet and 116 feet, but their ratios are still the same. You're comparing in tangent, that opposite over adjacent, you're comparing apples to apples, which is 1. Our second special right triangle is a 30-60 90-degree right triangle, and it also has relationships there. So what I'm going to do to derive or show this relationship is I'm just going to sketch out an equilateral triangle, which is 60 by 60 by 60. So each side length is going to be the same since equal angular triangles are also equilateral, and I'll let each side length be 2x. I don't know what the length is. I could call each side length x. I'll call it 2x for a reason that'll be obvious in just a second. So what I'm going to do now is draw an altitude straight down from this angle. And what's really nice about equilateral triangles like this and equiangular triangles like this, an altitude also serves as an angle bisector, as a perpendicular bisector. It just cuts everything in half. So what we now have is this angle here, which is 30 degrees, this angle right here, which is 30 degrees, and this side, which is cut in half now, which was originally 2x as a whole, now becomes 1x and 1x. So let me just get rid of this. And now I've got this 30, 60, 90 degree right triangle. The side opposite 30 is x. The side opposite the right angle, or the hypotenuse, is now twice x. And what I want to do now is find out what the side length opposite 60 degrees is. I'll use Pythagorean theorem. So this is x squared plus y squared equals 2x squared, which is now x squared plus y squared equals 4x squared. Let me subtract x squared on both sides, and I get y squared equals 3x squared, which, taking the square root of both sides, the square root of 3x squared is the square root of 3, and the square root of x squared is x. So now we can say that the side opposite the 60 degree angle is x square roots of 3. In other words, the relationship in a 30, 60, 90 degree triangle is the hypotenuse is twice as long as the shorter leg. The shorter leg is the leg opposite the smallest angle. And the other leg is the square root of 3 times as long as the shorter leg. Or in other words, a quick example, if I were to give you a 30, 60, 90 degree triangle, if the side opposite 3 was 5 inches, then the hypotenuse would be 10 inches, and the side opposite 60 would be 5 square roots of 3 inches. If I had another 30, 60, 90 degree triangle, and I said, hey, the hypotenuse is 16 feet long, then the side opposite the 30 degree angle would only be 8 feet, because the hypotenuse is twice as long as the shorter leg, and then the side opposite 60 would be 8 square roots of 3 feet long. So now, if I wanted to find the sine of a 30 degree angle, the sine of a 30 degree angle, sine would be opposite over the hypotenuse, 8 over 16. I'll just write it. The sine of 30 degrees is opposite over the hypotenuse. Watch this. What about if I do the sine of this 30 degree angle? So the sine of 30 degrees right here would be opposite over the hypotenuse. And what do you notice that the sine of any 30 degree angle is? 1/2, 1/2. The sine of 30 degrees is 1/2. Because in any 30, 60, 90 degree right triangle, hey, that side opposite 30 degrees is half that of the hypotenuse. Now, granted, the cosine of 30 degrees would be 5 over the square root of 3 over 10, which is 2 over the square root of 3. Well, I said that wrong. Oh, man, I did the secant. You got to make sure you're right. Put your finger on it. The cosine of 30 degrees is adjacent over the hypotenuse. So that is adjacent over the hypotenuse, which is the square root of 3 over 2. So be careful. Put your finger on them. Say the trig ratio out loud to yourself and triple check yourself. Last but not least, we've got these. This is pretty much the bulk of section 7.3. Watch this video several times. Know these special right triangles like the back of your naughty little head. And I'll show you one more example. So if I were to give you just a regular old triangle that has a 27 degree angle right there, and the hypotenuse is, say, 11 inches long, and I wanted to find out that missing side length, we put our finger on the angle, and we say, hey, what have we got? Oh, I'm looking for the opposite leg over the hypotenuse. Opposite hypotenuse. Some old hippie. So I want to use the sine of 27 degrees, which is x over 11. You're saying, well, could you use the cosine of 27? No, because we don't know what that side length is. Now, if you want to find the acute angle to, the complementary acute angle to this one right here, and then use a different trig ratio, then knock yourself out. But as written, we're looking for the opposite given the hypotenuse. Multiply both sides by 11. And this is when you know you have to use a calculator. If this angle is not 30 degrees, 60 degrees, or 45 degrees, you're going to pick up your calculator and type in 11 times the sine of 27. Just make sure your calculator is in degree mode. 11 times the sine of 27 degrees is roughly, in this case, 5 inches inside, which makes sense. You want to make sure that this leg is smaller than the hypotenuse. And if we start looking at around 27 degrees, that's a lot less, that's a little bit less than 30. And at opposite of 30-degree angle, it's half. So this one should definitely be less than half of 11, which it is. So it makes sense. So once again, as you're going through this course, I get it. Some of you skipped over the videos because I can see who's watching them and who's not. And you're going straight to the quizzes and using calculators. You're not learning trig. If it's a 30-degree angle, a 45, or 60-degree angle, and in time, other angle measures, you should not be using a calculator. So, trust me, don't take shortcuts right now. You're trying to figure out what you want to do for the rest of your life. And that's not something you want to take a shortcut at. So learn this material. Email me. Some of you are emailing me quite a bit. Watch these videos with me in it several times and study hard. Read the section. If you don't like the video, it's in the book. It's like ragu. It's in there. See you next week.